Okay, let us see one of the numerical based on the quiescent point and DC load line, right? Here, yeah, we have a image I, right? A diagram where I is a circuit, right? For this particular transistor, right? And for this transistor with beta equals to 100, right? Which is biased by base resistor, okay? And we have to draw the DC line and we have to determine the operating point. And what is the stability factor for this that we have to calculate, right? So for this circuit, we have to draw this, yeah, DC load line, right? And this quiescent point we have to calculate, right? So we will try to calculate the first quiescent point, right? So quiescent point is nothing but IC and VC, value of IC, right? Value of IC and value of VC that we have to calculate, right? Yeah. So what has been provided is that VCC equals to 6 volt, right? And RB is equal to here 530 volt. RC is 2 kilovolt, right? Yeah. Okay. And for calculating this IC, right, we have to apply a particular case here along this circuit, right? So we have a circuit that is yeah here from this VCC, then this resistance, then this yeah collector to emitter voltage, right, and this ground, right. So this yeah this is going to form a circuit, right, from VCC, these resistors RC, then this from this collector to emitter voltage to this right. Okay. So how we can write this equation for, right. So we have to calculate suppose VCE, that is this collector to emitter voltage, right, collector to emitter voltage. So how much voltage is going to be there? So whenever we are going to apply certain voltage here, right, certain amount of voltage should be consumed by this, and the remaining voltage will be appearing across the collector to emitter. So how we will apply the Kirchhoff's voltage law, that should be like how VCC plus the voltage across these resistors, that is equals to RC into IC plus C, right? VCC equals to what? This voltage across resistors, that is IC into RC plus VCE, or VCE equals to VCC minus RCIC. So VCC minus RC, that we have to form, right? So definitely, uh, suppose we have to calculate the minimum and maximum values of this line, right? So we will put IC equals to 0 first, right? So if we put IC equals to 0, so we will get the maximum value of VC equals to 6 volt. Okay, VC equals to 6 volt. Okay, right? And similarly, if we put value of VC equals to 0, so value of VC equals to 0, we will get IC equals to what? Yeah, yeah, VCC by RC, right? If you put VC equals to 0, so ICRC equals to VCC, or IC equals to VCC by RC. So value of IC will be 3 milliampere. Okay, so this will yeah will provide us the 2 points of DC load line. Okay, so we will plot this 3 milliampere here for 0 VC, right? This was 1 point at 7 point is IC equals to 0 and VCC is 6. So VC, if VCC is 6 and this IC is 0. So we have 2 points. We will join these 2 points, right? And so this port A and B will be load line. So this red one. Okay. Okay. Yeah. Okay. Now, yeah, we have to calculate the quiescent point Q, right? So yeah, how we are going to calculate? First, we have to calculate the value of I, for whatever the resistance in this base is applied, right? So according to the value of IB, we have to calculate the value of IC and VC. Okay. So yeah, how we are going to calculate them? First, we have to observe the circuit at this input, right? for base. So what is the circuit? From VCC it is yeah, this resistors that 530 volt, 530 kilo ohm resistor, which is the base resistor, and that this circuit, right? This circuit is to form uh, the input circuit for this transistor, and for this complete circuit, this circuit like this, we have to form the equation with KVL, right? So the equation becomes right like this, right? VCC equals to IBRB plus VB, right? VCC, we will be providing this IBRB and VB. Okay? Yeah. So maybe we are aware that VB's value is 0.7, right? Just we have to put that value and we have to calculate the value of IB. So IB equals to VCC minus VB upon RB is equal to 6 minus 0.7. 0.7 is the value of VB. Yeah, threshold voltage. Yeah, value of VB is 0.7. That we have to remove. And value of RB, that is below, right? That we put here and we get the value of IB, right? Now, for this value of IB, we have to calculate the value of IC, right? So what we have to formula, the collector current, that is equals to what, a beta into IB, right? So beta into IB is going to be the value of this collector current, right? So after putting, we get this value 1 milliampere. Now, collector to emitter voltage for this particular IB, right? For particular IB. So how we are going to calculate? So same equation that we have already. VCC minus ICRC, but now instead we will put here value of IC, that was 1 milliampere. We calculated with this value of IB, right? We will put the value of IC for this IB, right? And yeah, after solving it, we will get this particular value. So 4 volt and 1 milliampere. So VCE value is 4 volt and IC value is 1 milliampere. So this is what the Q center value of VCE and value of IC, right? That we are going to plot here. So on, and of course that value is always going to be on this load line that we have to remove 4 volt and 1 milliampere, right? Okay, so that was the Q point and DC load line calculation, right? Now, stability factor. Okay, so for particular transistor, right? We can, yeah, that stability factor is basically calculated as beta plus 1. Okay, so this will give the answer 101, right? That is due to the stability factor of this particular transistor.